Welcome everyone to the fourth DWL workshop and its RIE webinar series. Welcome to webinar 6 out of 8. Before we start, I'd like to do a few acknowledgements. Sorry about that. First, I wish to acknowledge the people of the Kulin Nations on whose land we are gathered here today, and I'd like to pay my respects to their elders, past, present, and emerging. Furthermore, I'd like to acknowledge the Australian National Fabrication Facility and its CEO, Jane Fitzpatrick, for their ongoing support of our workshop. Of course, also I'd like to acknowledge all our panelists who helped putting together the RIE Edge webinar series. And our sister conferences and workshops, the Heidelberg or the Zurich Nanofabrication Day, sorry, the 3Beams meeting, NanoFab UK, and the Mabel meeting. And a big shout out to all the members of the organizing committee for all their hard work making the workshop and the Edge webinar series happening. And this brings us to today's webinar, presented by Nick Chittock from Oxford Instruments, using the right tool for the job, comparing ALE, RIE, and IBE. Excuse me. So before I introduce our speaker, I also like to acknowledge NanoVacuum for their sponsoring of this webinar and also for the ongoing support of the workshop. So thank you very much, James, and thank you, NanoVacuum. All right. Our speaker today is Nick Chittock. Nick studied at the University of Exeter, including a year at the University of Wollongong during his master's before joining Oxford Instruments Plasma Technology as an ALD application technician. After a short time there, Nick moved back to academia and gained his PhD working in the Plasma and Materials Processing Group of Professor Irving Kessels at the Eindhoven University of Technology, specializing in atomic layer edge ALE and working in collaboration with Oxford Instruments Plasma Technology on development of new hardware and processes. While studying, Nick managed the ALE page of the Atomic Limits
website, going on?
Atomic website, which acts as an open source repository of ALE processes for the community. Since finishing his PhD, Nick has moved back to Oxford Instruments Plasma Technology, where he now works as the quantum market specialist, focusing on how the different tools can be leveraged to improve device fabrication for quantum applications. I'm going to stop sharing. And Nick, the stage is yours.
Yes, thank you very much for the introduction. Yeah, it's great to have the opportunity to present to all of you guys here, and thank you very much to the ANF for inviting me to give this talk. I'm glad I could join you remotely, and unfortunately, I couldn't be over in Australia again, but hopefully I'll be able to go over sometime soon and meet you all in person. As Michael said, my talk today will be the right tool for the job, so I'll be looking at comparing a few different ways of etching material. So I'll be comparing ion beam etching, reactive ion etching, and atomic layer etching, and looking at where there are benefits and potentially some drawbacks of using certain processes for different applications. As James mentioned, I work at Oxford Instruments, so I'll also talk a little bit about what it is we do as well. But I think an interesting thing to think about first is, what do I mean when I say using the right tool for the job? So there are a few things in life where instinctively we know exactly what would be the right tool for the right job. So if you're trying to dig a hole and someone says the job is to dig this really big foundation for a building, straight away you go, okay, I need a digger. Similarly, if you're digging a hole in your back garden, you want to put in a little pond or you want to do some gardening, you'll be, oh, I'll just use a shovel, it's pretty small, easy to dig through. And if you're trying to do some very fine scale controlled digging, say for like archaeology or digging small things out of the ground, you might want to use a small trowel. And for atomic scale process, and well, so for a lot of the things in here, there'll be similar questions that you would ask. So how big is the hole that you're wanting to dig? What will you be digging out? How quickly do you need it dug? And sometimes you might be asking why. And it's interesting that a lot of these questions that we would ask for kind of this macro scale problem of digging a big hole, they're also very similar to the questions that we actually ask when people come to us and say, oh, I'd like to etch such and such material for some kind of application. And so I think it's interesting to think about specific tasks and think of them in the context in which they need to be done. And so you need to have the correct tool for the correct job to make sure you actually hit the desired specification. And also when we think about doing complex tasks, you're going to need to be using that full toolbox as well. So to take the archaeology as an example, you're going to want to do the bulk of your etching with a much bigger tool and then do that final kind of small scale controlled etching with your trowel. Because if you come in with that big digger, you're probably going to destroy whatever it is you're actually trying to look at that's in the ground. So that's going to be kind of the main idea for my talk, is thinking about how we can use the right tools to get the desired outcome that we want. And so my talk will have this kind of structure. So unfortunately, because I am in industry, I have to give a little bit of a background of the company that I work for. I'll then give a bit of an overview of etching in general. So it sounds like there's been some very good webinars so far. So it sounds like you'll all be experts, but I'll go through a little bit of background just in case you missed a few of them. And then I'll go in and compare the 3 different types of etching we talked about. And then I'll end with a short summary. I hope that many of you already know who Oxford Instruments are, but if you don't, we're a big group of companies. So you can see the companies listed across the top there. So I work at Oxford Instruments Plasma Technology, and we're primarily focusing on device fabrication. So looking at lots of different materials processing techniques and how we can utilize those to make devices for myriad applications. So we work with people in kind of ranging from quantum, MEMS, photonics, power semi, like all over the world. And then there's also our sister companies who primarily focus in materials characterization. So there's a nice synergy there between kind of what we do with the material synthesis and processing and what they do with then characterizing those materials. Oxford Instruments, as I mentioned, is a global company. So we're actually based in the UK. So I'm actually based out of the Bristol, UK office. At the moment, I'm actually in Denver, which I think is somewhere over here. But yeah, usually I'm based out of our head office for plasma technology, which is based out of the UK. But I would like to also point out that we do have an office in Melbourne now as well. So we have some service and support. And we also have Nanovac, who will represent us in Australia as well. And I would also encourage, if anyone does happen to find themselves in the UK, I'd encourage you to come and check out our new factory. I think Michael mentioned a few of his colleagues were there the other week. And it's a great new facility. So we had a big investment of money. So we built this nice shiny new factory you can see in the top right here. And the really cool thing about it, from my point of view at least, is the massive new clean room that we've got. So it's an ISO 5.6, which means a class 100, class 1000 clean room. So it's a nice big space, lots of equipment to work with and lots of tools to develop new processes on. And you can see here a few of the application spaces that I mentioned that we typically work in. And I'd just like to stress as well that we've been around for over 40 years now, so we've got a lot of expertise and a lot of knowledge built up within the company, and we'd like to leverage that in helping you kind of achieve whatever it is that you want to do with our tools. And the tool set that we have at the moment, you can see on the right here, and this is actually one of the cluster setups with a few different tools around the outside. So the talk today will primarily focus on the top 3 ones that we can see here. So the etching tools, so the ion beam tool, the CCP RIE tool, and the ICP RIE and ALE tool that we do. I would also I'd just like to mention as well that we also do CVD and ALD as well. So we do both the deposition and the etching. But as I said, today I should be focusing on these 3 that you can see top. So that was a very, very quick run through of what Oxford Instruments is. I know it's the slightly boring bit, but my bosses insist that I talk a little bit about the company when I do these kind of things, so I have to get through it. And I'll now move on to talking a little bit about kind of give an overview of etching and how it's kind of progressed over the years. I think etching is one of these technologies, maybe a bit like fire, that has kind of been fundamental to humanity for a very long time. And it's always been a way of kind of transferring knowledge kind of from one generation to another. So I've kind of plotted here, so as a function of time, and the feature scales that we've been able to etch certain things. So some of the earliest reportings of etching that you can see, so digging through some archaeology papers, is people describing hunting with dogs and scratching this into rocks and kind of showing how different hunting techniques can be used to basically pass that down through generations to generations and communicate stories to each other. And that would typically be done with a sharp rock and just kind of hacking that into a flat surface. In the intervening few thousands of years, we got a little bit better at this. And one of the so in the golden era, the Renaissance era in the Netherlands, they started getting very good at this kind of print lithography process. So they were kind of etching these designs into metal plates. And so you can see kind of very basic schematic on the right here. So they'd start out with typically like a copper plate. They would put some kind of mask onto this plate. They would then use a very fine needle to scratch whatever the pattern is. So here, this is a Rembrandt. I can't remember the exact one it is, but a Rembrandt painting. So they scratch the pattern that they want into the mask. They then put this into an acid solution, and it etches away where there isn't the mask. They then clean away the mask and fill those recesses with ink, which can then be printed onto a canvas. And I thought this was quite interesting because it has a lot of parallels to very early semiconductor manufacturing when we think about it. So a lot of kind of wet etching and using mask layers and transferring that into one layer after another. And it's quite interesting seeing that the techniques they use, kind of a lot of that transferred over to early semiconductor manufacturing. I imagine many of you are very familiar with the fact that we moved beyond just using wet etching. So you can probably see from the image in the middle here, the problem with wet etching is that you kind of isotropically etch away material, and it limits how close together you can put different features on your wafer. And so one of the big things that allowed us to kind of progress and get smaller and smaller devices to go beyond this kind of 10 micrometer node was the introduction of plasma etching, and that allowed us to do much more vertical etching and kind of pack everything in a little bit tighter. And since then, combining our advanced etching techniques with both advances in deposition and lithography, we've been able to push this further and further. So we've gone now towards kind of this 3D scaling era that we talk about. So you may be familiar with kind of FinFET structures. And these are actually kind of in the phones that we're using already. And we're now in the process of transitioning towards these 3D structures as well. So you can see here the gate-all-around structure, which is kind of the next progression beyond the FinFET. And even beyond this as well, people are looking at things like fork sheet structures and stacking to the complementary. So basically stacking your NMOS and PMOS on top of each other in this gate-all-around. It's incredible what people are planning to do. And what's interesting is the etch process is going to be integral to kind of all of that advancement as well. So including how it's helped us get to this point, it's going to help us to get even further again as well. An interesting thing to think about as well when we're talking about etching is the directionality that we achieve with the etching. So it's, I think, an important concept to kind of wrap our heads around. So when we're talking about etching, we kind of generally talk about two different varieties. We can talk about anisotropic etching, and this is what allows us to make kind of etch wells and trenches and vertical features into a structure. So you can see on the left here to etch this isolation, the shallow trench isolation. You do an anisotropic etch, and that would typically look something like this on the right. So very, very simply schematically shown. And then we also quite often do isotropic etches as well. And for instance, this would be used to kind of release these nanowires. So you can see that schematically again on the right here. So we see that the isotropic etch allows us to remove material in between the layers and release those nanowires. And I think what's really incredible is that the gap between these nanowires is only about 10 nanometers. And I think that's something that still blows my mind, like working on these kind of things. It's the scales that we're talking about nowadays are truly kind of mind-blowing. So yeah, I think it's very interesting to see. And improvements in etch technology have really kind of powered the modern world that we see around us today. So I'm sure you're all familiar with Moore's law, and it's what allowed us to go from these kind of large scale structures that you see on the left here, so kind of increasing transistor count year on year and going from these kind of planar structures towards these highly scaled 3D architectures as well. But I think it's important to mention that even at this very front end scale, we also need to kind of think a little bit further back as well, because your device isn't just the transistor, it's the entire stack. You need to be able to kind of fabricate all of these layers on top of each other. So you've got this transistor structure you see here, but when we look into the device, it's actually only this very small bit of silicon right in front here. And it even goes a step back further again. So it's not just focusing on one layer and making things smaller and smaller. We kind of need to make sure that we have good processes throughout the entire stack to make sure that we get a good device at the end. And it's interesting to think about the different constraints and goals that we have at each layer and how that impacts upon the type of etching we do. And as I mentioned at the beginning, it kind of becomes a game of combining your full toolbox to make sure that you can fabricate the full device. So using both your digger, your spade, and your trowel to make sure that you're etching in the right way at the right point. I would like to stress as well that it's not just, so this was very kind of CMOS and silicon focused, but I would like to mention as well that micro and nano fabrication is much more than just kind of the field effect transistors and memory devices that people are working on. I think micro and nanofabrication is such an enabling technology across a wide variety of application spaces. So we can see nanoelectronics is obviously a big one, but we've got photonics, quantum technology, photovoltaics, and even towards like bio applications as well. And it's great to see that a lot of these cutting edge applications can also be transferred almost directly across to these other applications as well. And I was actually going through some kind of old papers that were done on Oxford Instruments tools, and I found this really interesting one where they made a antimicrobial coating using diamond coated silicon, black silicon. And so basically you etch these very fine nanopillars into silicon, coat them with diamond, and then they're so small and the orientation that you have them in, bacteria simply can't survive on them. So you can see here, there's a dead bacteria that's being pierced by one of these nanopillars. So it really goes to show that kind of microfabrication, nanofabrication can be used across such a wide range of application spaces. It's, yeah, just an incredible thing. So when we look at the different etching technologies that we can use in micro and nanofabrication, they can kind of very broadly be and very loosely kind of defined in terms of the etch rate that you have and the kind of low damage smoothness that you're able to achieve. So we can see how they all kind of fall down in this little table here. So we have, I've also kind of cheated and split reactive ion etching into a few different categories because RIE is a very diverse and versatile tool. So there's a few different flavors, but you can broadly see, like, if you want to have a very high etch rate, you're best to use a reactive ion etch process. But if you're wanting to kind of get a very controlled process, you're probably going to have to go a bit slower, but you'll have a much smoother film. So there you probably want to use atomic layer etching. So again, it really kind of depends exactly what your application space is and what your end goal is as to what kind of etching process you use. I would also like to say, so my background is atomic layer etching and everyone complains that it's too slow. We are working on making it better and faster. So come back in a few years and it'll be up there with ALD and high volume manufacturing as well. But yeah, it's a newer technique and still being developed a little bit. But there are things going on there. So that was a very kind of brief overview of just kind of etching as a bit of a history. I'll now go into kind of the main part of my talk, going through the kind of three different etching techniques that I highlighted at the beginning. So I'll start off with ion beam etching. And this is quite an old etching technique, to be fair. It's quite simple. I think Lena's talk last week, but simple in concept, but the devil is always in the detail. So Lena gave, I think, a very nice webinar for the last webinar in this series. She talked a lot about what happens when your ions interact with your surfaces. So fortunately, everyone's a specialist in that now. I won't have to go into too much detail, hopefully. But ion beam etching, so you can see a schematic of the tool on the right here. And very simply, it's a kind of ICP plasma source on the right, and then a few accelerating grids. And then those ions are accelerated into whatever the sample is that you're trying to etch. Ion beam etching is a physical technique. So it's physically sputtering away material, as we learned from the last webinar as well. And what's nice about ion beam etching is it etches pretty much all materials. So if you fire argonines in with enough energy, you're probably going to be able to sputter whatever it is that you're trying to etch. On top of that, it's very low contamination because the argonines themselves are inert. So you might introduce some argon into your film, but generally the contamination that you see with these processes is very low because the argonines are inert, but also because the operating pressures of the tool are also very low. So it's typically around, I think, like 10 to the -8 torr for the base pressure of these kind of tools. And that's because you need to have a very long mean-free path for the ion. So when the ion comes out of your ICP source, you want to make sure it's not colliding with any gas phase molecules before it hits your substrate, as that will kind of scatter them off and kind of reduce the efficiency of the process. I should mention as well that one of the interesting things for this is that samples, so the actual table itself, the substrate holder, can be rotated as we're doing the etching. And I'll talk a little bit about how that can be very beneficial for processing later on as well. And one of the interesting things as well is that you can slant this substrate holder as well. So that can also be very beneficial for removing some unwanted side processes in your etch. Again, talk a little bit about that later. They can also be used to just etch kind of slanted structures into your I mentioned that it is primarily done with inert argonines, but you can also look to use chemistry to enhance the etching rates that you're able to achieve and also improve the selectivities. So that would typically be called reactive ion beam etching. And there you would add some sort of reactive chemistry into the ICP plasma. So you'd be using chemical ions as well, so things like fluorine and chlorine. But you can also have it so you can have a gas ring just above where your substrate is, and there you can also inject in chemistry in the gas phase, and that can be used to kind of absorb onto your surface and help with the chemically assist you're performing, again helping to improve the etch rate and the selectivity. Ion beam etching is used in a lot of different applications, primarily for kind of metal stack etching. One of the major markets we're seeing at the moment is actually slanted etching for augmented reality devices. I'll talk a little bit more about that later on as well. But essentially being able to etch, instead of having kind of thin structures that are vertical, you can have them at a slant, and that's really useful for that augmented reality. And then, yeah, laser facet etching, MRAM, so it's been used for many, many years for these magnetic random access memory and magnetic tunnel junctions. And then also, yeah, for photonics and high temperature superconductors as well. This is just a little bit of the kind of specification of our tool, but I won't dwell too much on this because there are other ion beam etching systems available. So you don't have to just use our system, although I think it's the best. There are other ion beam systems. But you can see, yeah, kind of one of the pictures of the tool down here. We process up to 8-inch samples, and we can do this with either mechanical with mechanical clamping, and we can either kind of cluster as a cassette. We can process 8-inch all the way down to 4-inch, and we can kind of process in a temperature range from about 10 to 300 degrees C. And you can see actually in the bottom left here, one of those slanted etches that I was talking about. So that's kind of non-vertical profiles. So when we talk about ion beam etching, what we're really talking about is just sputtering the surface of the material. So as I mentioned, Lena's already kind of made you experts in this, so I won't talk too long about this, but there are many different complex interactions that are going on the surface. When an ion impacts upon the surface, you can see there's a myriad of different things that can go on at the surface. But the main one that we're interested in for ion beam etching is this sputter reaction driven by the collision cascade. We can see that a bit clearly in this figure on the right. So when we're trying to sputter material, we'll have an instant ion come in. It'll collide with the surface atom, kind of recoil it into the surface, and the momentum will be transferred to other atoms in the near surface, and eventually it'll be redirected out of the surface again. So through this collisional cascade, where you have one ion come in, eventually the momentum is redirected out of the surface, allowing G to continue. What's interesting is that I've kind of very simplistically shown this as a kind of one ion in, one ion out sort of situation. But typically we see that that's not really the case until you get to kind of very high ion energies. And for some materials, in fact, it stays very low even towards higher energies. So when we look at the instant ion energy, so that's what's plotted along the bottom here, as and also look at it for the sputter yield. So on the y-axis, we're showing sputter yield. And we can see this for a few different materials. And so we see that the sputter yields, all of the lines have this kind of almost square root dependence that we see. And this is because when one ion comes in, typically you're not getting that kind of nice unitary momentum transfer, and quite often it will be kind of sub one. So you'll have to send in multiple ions to achieve getting an ion out at the end of the day. So the ion energy is very important in terms of kind of what influences our sputter rate. So typically, unsurprisingly, you'll see that higher ion energies typically result in faster sputter rates. What's interesting as well is that the mass of your instant ion can also play a big role. So the mass of both your target and the ion that you're using to sputter. So kind of based on this momentum transfer equation. And I've actually plotted this out for a few different, so that, well, I've actually stolen this table, but it's from the textbook at the bottom here, but I've kind of replotted it myself here. And it shows very nicely, so for a few different ions, so all the inert ions we can see at the top here, and their mass, so increasing mass left to right. So looking at different ion masses and different target masses, and we see that there's generally a kind of increasing kind of diagonal trend in terms of having higher sputter yield when there's a good match between the target mass and the ion mass. So we can see very nicely for the copper that when we use argon or krypton, which have a similar mass, we're able to get a higher sputter yield, a higher etch rate, because that momentum transfer is more efficient because the target mass and the ion mass have a very similar energy. In practice, we mostly use argon because it is the cheapest gas to use and one of the easiest ones to work with. But it is interesting to think about how the incident ion that you're using can affect the sputter rate that you can get as well. And then lastly, angle of incidence is very important. So I mentioned that we can vary the angle of the table in our tool. And it's very interesting if you plot the angle of incidence as a function of sputter yield. Plot the sputter yield as a function of angle of incidence. And we see that there's this increasing trend up to a point. So we get kind of maximum sputter efficiency when we kind of have, I think for most materials, between kind of 30 to kind of 70 degrees. But then if you get to the point where you actually have the ion, so if you imagine 0 is coming straight down, if you have an ion coming in at near 90, it's actually just kind of glance off the surface rather than cause any sputtering. So it's kind of ideal angles at which you can maximize the etching that you're able to achieve. So this is kind of the three main things that influence sputter rates. But again, you're already all experts in that after the last talk. So I'll go into a little bit more about how we kind of generate these ions. So you can see in a bit more detail a schematic of a ion beam etching tool in the bottom left here. So we have our ICP source on the right. So this is where we generate our plasma. We have our grid set. So this is typically for our tools, we have 3 grids. And the ions are kind of extracted from the plasma and accelerated by the grid and then incident upon the substrate, which is on the substrate holder, which, as I mentioned, can be kind of tilted and rotated. As I mentioned, yeah, we have very low background pressures, and when we're operating, we operate at kind of 10 to the minus 4. And this allows us to have a very long mean-free path for the ions so that they're not colliding as they make their way towards the sample to do the etching. This ensures that we get a nice high ion energy, but also that we don't get a wide distribution in our angle of incidence in our ions. And we can see in more detail on the right here. So this is the screen. So it's this kind of 3 electrode setup that we have here. So we have our screen, which looks like just a big disc with holes in it, basically. I think it's typically made out of graphite or molybdenum. And we have a few different voltages. So we have kind of a screen, which extracts the ions from the plasma. We have the accelerator, which accelerates the ions, and then the grounded one as well. So the plasma source here is a low temperature plasma. So it's ICP plasma, and we use the grids to extract the ions from that. And we're basically trying to make sure that we have a nicely collimated beam with a little bit of kind of dispersion that you can see here. And so the dispersion means that we actually have overlapping little dots, basically, of where the argon ions come through. Because you can imagine if you used a screen and you had a perfectly collimated beam, you'd actually only be etching in small patches, and there'd be spots in between all these different holes where you'd actually get no etching. So you need to have a little bit of beam divergence so that all of your spots overlap. And then after the accelerator grid, we also have a neutralizer, and this makes sure that we're not kind of getting any charging effects going on both at the substrate and on the grids themselves. So yeah, basically neutralizes the ions before they get to the surface, not charging up the sample that's being etched, which would eventually lead to non-idealities in our etching process. The ion sources that are typically used are between 15 centimeters and 30 centimeters. Ideally, your ion source needs to be, so for our systems, they're 15 and 30 centimeters because your source needs to be bigger than the wafer that you're planning to etch. Because you can imagine if you were trying to etch an 8-inch or 20 centimeter wafer, and your ion source was only, say, 10 centimeters, you'd end up just etching in the middle and having no etching at the edge. So you need to make sure your ion source is bigger than the sample that you're planning to etch. You can see a few different parameters that we're able to achieve. They're broadly similar for the different source diameters, so there's not too much difference. As I mentioned, going through at the beginning, there's a few different types of iron-beam etching. So there's kind of the vanilla version, which is just basic, using typically just argon ions. So using these inert argon ions. As I mentioned, we can rotate the substrate up to kind of 20 RPM, and we're also able to tilt the substrate as well. So that's a very basic flavor of iron beam etching. We can also do reactive iron beam etching. So that can help with selectivity and improving etch rates. And there it's the introducing the ions in the ICP plasma. And we can also do the chemically assisted iron beam etching as well. And that's where we introduce the chemistry actually at the substrate itself, rather than in the ICP source. There can be some potential issues when using iron beam etching that it's important to keep an eye on. So you can get trenching effects occurring. So this is where the ions coming in. So if you're trying to etch vertically down into a feature, you can have it where an ion comes in and glances off a sidewall and gets reflected to the surface, as we can see in the image here. And this can lead to getting kind of enhanced etching. So you have a slightly higher flux in the corners, so you get a slightly higher etch rate in the regions. We can also get fencing. So because you are relying on the inert chemistry, the material that you're etching can actually sometimes redeposit on the sidewalls. So you can see here the iron comes in, we sputter away some of the surface material, and instead of being kind of pumped away, it actually lands onto the photoresist and actually deposits there. And when we do the photoresist strip, can actually maintain that structure. And this is what we call fencing, because when you look at it in the SEM, you see basically a nice fence on top of the feature, which ideally shouldn't be there. So it's quite an annoying one to deal with. And we can also sometimes see roughness. So crystal orientations, if you have a crystalline material, so a polycrystalline material, depending on what orientation you have on the surface, they may etch at slightly different rates, and this can lead to kind of roughness surface. Fortunately, there's a few ways to deal with that. So by using the sample rotation and the tilting, this allows us, so you can see in the bottom right here, so the typical kind of 0 degree instance, we can also kind of increase it to 30 degrees. And you can also look at doing some etches where you do the main etch at one angle and then do a kind of cleaning process at a slightly sharper angle, again, to help kind of remove material. So what this does, so for the trenching, by some, and I didn't mention about the rotation as well, that just makes sure that for the roughness that you're kind of getting, you're not getting ions at only one particular angle coming into your surface. So the sample rotation and tilt helps with the trenching because it basically evens out any additional ion dosing, so you get a more uniform etching. For fencing, the tilting allows it, so instead of the ion coming in vertically, if you had it tilted, the ion would come in and hit your sidewall. So this helps actually sputter away any fencing that could occur, so you don't get that buildup on your mask or photoresist. And the roughness, again, as I mentioned, yeah, so changing the angles ensures that different orientations get ions from loads of different angles. And this basically kind of evens everything out rather than just having it at one particular angle and getting one crystal orientation that's preferentially etched over others. So that kind of lets us overcome some of those issues. So there are things to think about when you are using iron beam etching, but there are ways to get around from using it. And so when we talk about iron beam etching, the main things that we look at for adjusting the process, so you can see on the left here, a few of the main processing parameters that we look into. So there's the beam current and the beam voltage. These are kind of adjusted by varying the grid voltage that you have in the ICP plasma. The accelerator voltage, again, this is set by the grid. The argon source, so again, just how much gas you're essentially flowing into the ICP. The RF power controls the density that you're getting within the ICP source, so kind of how many ions you're generating in the source. One thing that we try to do is make it low damage. So we try to use a low beam voltage to kind of minimize the damage that we're getting. And if we want to do high rate, we'll go very high beam current, use a high beam voltage. And as I mentioned previously, for RIE and CAIBE, we add those reactive gases, which helps us to change both the etch rate and selectivity to different mask material. So a typical process, so here I'm showing an example of a low rate silicon oxide etching process, and you can see the different beam parameters that we're using here. So we start off etching in this orientation, and then going to change to a slightly different orientation, well, different process conditions. And we can see the how the beam current affects the etch rate. So we have increasing beam current on the bottom in milliamps. So the increasing beam current basically increases the etch rate we're able to achieve. So unsurprisingly, kind of increasing the beam current leads to a higher etch rate. And what's nice is that the etching process is highly uniform as well. So we can get around kind of, well, as we see here, less than 1% uniformity, sorry, non-uniformity across the wafer. So we're getting good etching at both sides of the wafer, and shows that it's a very uniform process. Gives a very nice etch rate. And the etch rate itself is kind of varies depending on the different beam parameters that we use. So on the beam current and the beam voltage, beam voltage. So as we go to higher beam voltages, we see we get a higher average etch rate. And so one of the things I mentioned at the beginning is that IBE, one of the benefits is that it etches many materials and can etch pretty much any material because you're just hitting something with argonines. But that does have the downside that selectivity can sometimes be quite hard. So when we're trying to etch, say, in this instance, this metallic film, we're having to use quite a thick resist to be able to etch through it because the selectivity between the two materials is typically around kind of 1-to-1, 2-to-1. And for some other materials as well. So for instance, the selectivity between if you're trying to etch tantalum silicon oxide mask, actually see that we get very low selectivities there as well. And so just as some examples of things that we can kind of etch with ion beam, so I mentioned it's very good for stacks of different materials. So on the top here, we can see a stack of all these different materials listed along the top. And ion beam etching is great because it just allows you to etch all the way through the different materials and not have to worry too much about the chemistry messing with the process. So you can imagine if you wanted to do this with reactive ion etching, you'd have to worry about how, say you're using a chlorine or a fluorine-based process, you'd have to worry about how that chemistry would impact on all these different layers in your stack. Whereas by using ion beam etching, you're able to etch through all of the materials in one shot without having to kind of unload the wafer, do a chamber clean, load the wafer back in, run a process. So it's really, really useful in that regard. We can see a PZT platinum silicon oxide stack and also a lithium niobate stack as well. So ion beam etching is used quite often for etching these kind of very hard to etch materials, such as lithium niobate. Because the argonines are very useful for that. But we're also able to etch things like quartz as well and slanted silicon, as I mentioned. So this slanted etch is very useful for augmented reality applications. And then also some examples of chemically assisted ion beam etching. So for gallium arsenide vertical cavity lasers, pixels, but also for indium phosphide etching as well. And you can see the nice kind of verticality and smooth sidewalls that we're able to achieve etching indium phosphide, which is typically quite a hard material to etch, but ion beam etching gives us a very nice profile as well. But one of the key things we need to think about is when do we actually want to stop doing the etching as well. So there's two different techniques that we typically use. So there's optical emission spectroscopy and secondary ion mass spectroscopy, depending a little bit on what you're trying to look at. So here we're comparing the two, looking at a 4-inch wafer etch of this stack of materials you can see at the top. And what's nice about both of these is that we can track the different signals of different constituent materials as we're doing the etch. And so we can know when we've kind of got to the, got through one layer and gone into the next one, and also finally etched all the way through the stack. So optical emission spectroscopy looks at kind of different wavelengths of light. So each element will have a characteristic wavelength that we'll look at. And SIMS physically looks at the ions that are being kind of detected coming off the surface. So get ejected. Whether you're using OES or SIMS depends a lot upon the material you're using, the process gases, and the open area in your mask. I think SIMS is typically a little bit more sensitive than OES. So if you've got a very small open area, you might want to use SIMS just because it's a little bit sensitive. But it really kind of depends exactly what application you're looking into as to which makes most sense to track your etching. As I mentioned, iron beam etching has been around for a while, so unsurprisingly, we have a huge library of materials to be etched. So if you are interested in see materials that you want to be able to etch a bit better, then yeah, reach out and I can put you in contact with some of our apps team who can hopefully help you out. So in summary for the iron beam etch section, it's a very useful process for etching multi-material stacks. So I mentioned this kind of complicated stack of materials. You can etch straight through it with argon beam, with the argon beam. The etching occurs by physical sputtering. So it allows us to have very low contamination processes. And as I mentioned, the sample rotation and tilting really allows us to overcome some of the process issues that we can sometimes see. But it can also be but you can also intentionally not do it and allow us to get these very interesting structures and these slanted gratings that you see here. I think with that, we can maybe take a short break before I then go and talk about the reactive ion etching and atomic layer etching. So I think, Michael, we mentioned maybe a 5-minute break or?
Sounds good, Nick.
Cool.
I think we're good to go, Nick, if you want to continue.
Okay, yeah. Cool. So that was a very kind of brief run through of what ion beam etching is, and hopefully kind of given some examples that people found interesting and hopefully learn a little bit about how the tool works if you haven't seen it before. I'll now continue the talk by going through reactive ion etching and then end with the atomic layer etching section. I imagine many people are already familiar with reactive ion etching as it's a very kind of versatile and widely used process. But I think it's interesting to kind of think about some of the basics of reactive ion etching. So as I mentioned, it's a workhorse used all over the place. And one of the most experiments done in reactive ion etching is this Coburn and Winters paper where they first kind of looked into and kind of targeted the synergy that you can achieve by combining the kind of physical ion sputtering component and the chemical component of etching. So in the bottom left here, we're seeing kind of the figure that I've taken from that original paper. So on the bottom, they're just plotting time, and on the y-axis, the etch rate. And at the beginning, they're only dosing the chemical component of the etching. So in this case, they're only dosing the xenon difluoride. And they see the silicon etch rate is pretty low, so a few angstrom per minute. They then turn on the argon ion beam, and they see that the etch rate jumps up massively and then stabilizes at a much higher etch rate, so around 60 angstrom per minute. But when they turn off the xenon difluoride exposure, they see the etch rate drops again rapidly down to only a few angstrom per minute again. And that's what reactive ion etching relies on, is that synergy between the kind of chemical component of the etching and the physical component of the etching. And we can kind of sort of see that on the right here. So you have your plasma, and it's contributing ions towards the surface, but it's also contributing chemistry towards the surface. And typically we'll see that you end up with a kind of mixed selvage layer as you do the etching. So I think David Graves gave a very nice kind of overview of how the surface looks kind of at the kind of molecular level as you're etching material, and you see you get that kind of disorder and mix layer as you etch the material away. But it's that mixing that allows you to get that high etch rate because it lowers the sputter threshold material. I've showed it very, very simply in that previous slide, what's going on at the surface when we have a plasma interacting with a material. In reality, it's a very, very complex process that's going on there. So you can see in the figure I'm showing in the middle here, all the different things you've got to think about as your plasma interacts, not only with the substrate itself, but also the chamber within which it's housed. So chamber condition is a really important thing when we're talking about reactive ion etching, because if you don't look after your chamber condition, you'll see that your etch will vary quite dramatically over time. So it's important both to kind of look at what's going on at your substrate, but also kind of consider what's happening in other parts of the chamber as well. And so when we look at the interaction, so we have lots of complex plasma physics and chemistry going on in the plasma itself. And then additionally, we also have very complex surface chemistry and plasma surface interactions. So there's lots of things to think about in reactive ion etching and when we go into kind of doing process stuff as well. Similar to ion beam etching, there are also many different, well, 3 different flavors of RIE very broadly. There's the kind of very basic systems, and these will be capacitively coupled plasma reactive ion etch systems. So your plasma is formed between the two parallel plates. You typically have kind of one powered electrode on which the substrate sits, and then you kind of got your grounded plate at the top. In our configuration, we have that where the gases come through as well. These are great systems because they're very compact and easy to use. One of the potential downside is that your ion flux and energy are linked, so it gives you a little less process kind of variability and ability to control the process, but they're very good at doing things like oxygen, ashing, and photoresist. A slightly more advanced version of the tool is an inductively coupled, or ICP, reactive ion etch system. So you can see that in the middle here. At Oxford Instruments, we have this as a kind of big ICP tube with the coils wrapped around the outside. I should also say you can get kind of planar ICP coil configurations as well. What's nice about these kind of remote ICP sources is that your ion density and ion energy are decoupled. So you can kind of strike your plasma in the tube up here. And then by varying the table bias, you can really tune in the ion energy that the substrate is seeing. And I'll talk a little bit about things interesting as well. And that biasing can also help us tune the isotropy of the etching we're able to achieve. So whether we get a fully vertical profile or whether we get kind of these interesting wavy structures. And then lastly, you can also do deep reactive ion etching. So this is a slightly specialized version really of ICP etching. So you have slightly higher plasma densities and you have kind of fast gas switching to enable you to do Bosch processing. What we do in our deep reactive etching systems. So Bosch processing is just switching back. And so when it comes to process requirements for reactive ion etching, there's a few things that we need to think about. So I've listed a few of the parameters in this table on the left here. So we need to think about one, kind of what etch depth are we looking at, what etch rate are we trying to achieve, what aspect ratio are we trying to etch to, what selectivity do we need? So this can both be to the mask itself, but also to other materials that chemistry is going to be seeing. So it might be that you're trying to etch one material on top of another, and you want to make sure that you etch and then stop onto that layer. So that's really important to think about what selectivity you'll be getting from one material to the other. Other things we kind of target as well are surface roughness. So typically we want this to be as low as possible. Although for the bacteria case I showed at the beginning, you actually want there to be very high surface roughness. So it's very interesting to sometimes think about how you often are tuning to improve one parameter, and then sometimes it's like, oh no, we want a completely different parameter in a different application. So it's interesting to see what different people want for different things. And then lastly, one of the things we often try to tune for is profile as well. So again, this varies depending on the application that you're interested in. So we can see on the right here, so this is for an algan indium phosphide meso etch. And some people want to have a sloped profile, and some people want to have a vertical meso structure. So it really kind of depends on the application space that you want. If you want a kind of sloped profile, one of the easiest ways to do that is just to prepare your mask already with the angle that you want to achieve. So you can see on in this etch, the mask itself was slightly slanted, whereas in this etch, there was a vertical mask. I won't go too much into that because we don't actually do the mask development ourselves. We only focus on the etching side of things as well. But what's interesting is that you can actually kind of create slanted structures, vertical structures. But if you play around with the chemistry as you're doing the etch, you can also create these kind of interesting, kind of varied profile structures. And I'll talk a little bit about that in the coming slides as well. But when it comes to trying to optimize for these different parameters, the main kind of process levers that we pull are the plasma chemistry, the ion energy, and the temperature at which we process. So talking first about the plasma chemistry, so you can tune this in a few different ways. One of the easiest ways to do this is by tuning the feed gas. So again, stealing from Coburn and Winters. So they did some great experiments in the early days looking at reactive ion etching. And they looked at how the fluorine to carbon ratio impacts upon the silicon etch rate, and also how the bias applied to the surface impacts the etch rate. And they found that basically if you have a higher fraction of fluorine to carbon, you're more likely to be in a high etching regime. Whereas if you change to a more kind of carbon rich plasma with a low bias applied to the substrate, you'll be in a more polymerization. So instead of getting etching, you'll just be kind of forming polymer on the surface of the material. So one of the easiest ways to kind of tune whether you're getting etching or not is to tune your fluorine to carbon ratio, but then you can also think about adjusting that even further by adding hydrogen or oxygen to your plasma to help with kind of slowing up or speeding down your etch. And you can also look at this as well. So people have demonstrated this for silicon germanium etching as well. So here we see changing ratio of adding C4F8 into a CF4 plasma. And they find that the etch rate is very low when they have a high amount of C4F8 because there's lots of carbons, there's lots of polymerization, so the etching is slowed down. And in fact, I think fully stops. But when they reduce that fraction of C4F8 in the plasma and have a more fluorine-rich plasma, they see that the etch rate rapidly increases. So it really shows that tuning the plasma chemistry can be a really easy way to kind of vary the etching that you're getting. People often also add, if you're doing a chlorine-based etch, they'll also quite often add BCl3 to your chemistry. So that the thinking there is that the BCl3 helps scavenge away oxygen and prevent brassing and reduce roughness. So that's what we can see on the right here. So this is looking at silicon carbide etching. And so you can see the starting surface is pretty rough. If you do the etch without the BCl3, you still get quite a lot of roughness in your surface. But if you add even small amounts of BCl3 into your chlorine plasma, you're able to kind of effectively scavenge away oxygen and prevent any silicon oxide forming, which can then lead towards kind of micromasking and brassing, increasing. It should be pointed out, though, that if you are using a very heavy polymer forming plasma to do your etching, you'll also have to think a lot more about the chamber conditioning that you're going to need to do. So I mentioned that you've also got to think about what's going on your chamber walls. So if you're doing a very polymer forming plasma, it's going to be building up on your walls, and you might find that your etch changes quite dramatically if you don't think about cleaning that away and about the chamber conditioning. One of the main things we can also, so with deep silicon reactive ion etching, their plasma chemistry is extremely important. So I mentioned the Bosch process, so that's switching back and forth between SF6 plasma and some kind of CF plasma. So during the Bosch process, you'll bias etch with SF6. So that etches kind of down into the material a bit. You'll then do a passivation, so intentionally form polymer on your surfaces. And then you'll do the directional etch again. And so switching back and forward between this anisotropic etch and then passivation, you're able to get a very fast etch rate, but you do actually end up causing scallops because the etch isn't perfectly anisotropic. And we can actually see that scalloping in this figure on the right here. So it's really useful because you can make these nice big trench structures. So for through silicon vias, for those kind of applications, deep silicon etching Bosch process is excellent, but it can leave this kind of wavy texture on the sidewalls. For some applications, that's absolutely fine. For other applications, we look into ways of removing these scallops. So you can do either an in situ dry process, or I think it's quite common now to do an oxygen plasma and then an HF dip to try and remove the scallops from the sidewalls. And you can also do mixed gas processing. So I mentioned if you vary the gas composition as you're doing your reactive ion etch process, you can vary the isotropy of your etching. So if you kind of drive it towards a more chemically driven etch, you can kind of get it to kind of undercut the mask a little bit. Then if you switch back to doing a purely kind of directional process again, you can get these kind of nice tapered structures that you see here. And in fact, in this case, we did that kind of more isotropic etch, went back to doing an anisotropic etch, and then went back to doing a slightly more isotropic etch again. So you get this kind of double kind of circle structure that you see on the right. You can also tune the plasma chemistry with your plasma power. So this is one of the great things about the ICP RIE system, is that you're able to kind of tune separately what's going on in your plasma and what's going on at the substrate. And typically a higher plasma power gives a great dissociation fraction in the plasma. So you get more ions and more radicals to help drive your etching process. So on the right here, we can see the ICP power, and we can see the effect that has on the etch rate of silicon carbide. So here they're using an SF6 oxygen plasma, and as they increase the ICP power, they see that they're getting a higher and higher etch rate. What's also interesting is that this can help with achieving the desired profile that you want. So I mentioned earlier on about trenching. So you see the, enhanced etching at the corners of the structure here. By going to a higher ICP power, they increase basically the chemical component of the etching. and it helps even out a little bit the profile that they're seeing, so you can get towards an actual nice square profile rather than having this mound of your feature. The next key thing that we can look at is the ion energy for tuning our process. So this is typically controlled by the table bias. So your substrate will be sitting kind of on the table here, and the table bias basically dictates the energy of the ions that are coming into it. So as you increase your substrate bias, you get a higher ion energy. And as we learned from this ion beam section, a higher ion energy typically equates to higher etch rates as well. So we can see on the right here, ion energy and the ion energy distribution function. So you can see as you go to higher and higher substrate bias voltages, see you get higher and higher peak ion energies as well. What's also interesting is that at the higher the higher substrate biases, you also get a kind of narrower distribution in your incident ions. So when you have a higher voltage, you'll get more directional etching, whereas if you do a much lower bias power, you actually get a slightly larger spread in your incident angle. So you'll get more ions kind of impacting the sidewalls of your feature. And so this is great. So this allows us to do things like etching these nice vertical profiles, but you do need to be slightly wary, because if you go too high in your ion energy, you can actually degrade selectivity, increase roughness, and induce surface damage. So on the right here, you can see a gallium nitride film that's being etched with reactive ion etching. I think they intentionally did it a little bit badly to kind of highlight this. But you can see that if you tune the RIE process wrong and use the too high in energy, you actually introduce a lot of roughness and damage into your material. And in fact, they showed that it degraded the crystalline quality of the algan underneath as well. So it's not just the material you're etching, that damage layer can actually propagate kind of, I think people have reported about 20 odd nanometers into the surface below as well. So it's not just the material you're etching, it can also be things underneath damaging. So you really need to make sure that you tune your ion energy to where it needs to be. Chamber pressure as well can be a very good way of controlling your ion energy. So going to higher chamber pressures typically increases the number of ions available. So when you're at very low pressures, if you increase the pressure slightly, you can get slightly higher flux. But if you go too high, you actually start to degrade the etch rate. So we see with increasing pressure beyond kind of around 10 millitorr on our systems, we see that the increasing pressure can actually degrade our ion flux, and we get much lower ion energies at the surface. So this is because you're getting more collisions before your ions actually impact onto the material. So they're being scattered and losing their energy, and therefore less effective etching. And so we see this trend both for ICP plasmas and also CCP plasmas. So we see at low pressure, so at around 3 Pascal, they have quite high ion energy. And then as they increase the pressure, so up to 30 Pascal, they see that the peak ion energy has decreased quite dramatically, both at the power. I mentioned, and I think Christophe Valle gave some very interesting slides on this during his webinar right at the start. So I think that was the first one in the series, looking at how you can do interesting things around playing around with your plasma pulsing. So you can look at source pulsing, bias pulsing, where you, so source pulsing is you just pulse the ICP on and off. Bias is where you kind of have a continuous source and then just pulse the bias power on and off. And then you can also think about doing this synchronized or asynchronously. And it's quite interesting how that can impact on the etching that you're achieving. And this is because the species that you have present in your plasma actually vary as a function of time. So we can see all the, so this is for kind of chlorine plasma, and we can see how the chlorine ions, how their density, as well as the electron temperature and density of electrons changes. So we see that there's different decay rates for the ions, different decay rates for the electrons as well. So if you're really trying to really fine tune a process, you can look into pulsing as a way to really target what species you need to etch. And people have demonstrated that it can be quite an interesting way to get around aspect ratio dependent etching. So ARDE. So typically you find that if you have very high aspect ratio structures and low aspect ratio structures next to each other on a sample, you'll see a much higher etch rate in the low aspect ratio compared to the high aspect ratio. And this pulse processing can be a way to mitigate that. Alternatively, people are also looking into alternative ways of controlling the ion energy, so using tailored waveform biasing. So this is a topic that's been around for a few years now. You can see in the bottom left here. I won't go into too much detail, but it is a very interesting way. So we saw earlier that broad distribution in ion energies that you got from the RF bias, but if you use the tailored waveform bias, you can get these very narrow distributions, even up to quite high ion energies. You can use this to very accurately determine sputter thresholds of different materials and improve your selectivity of your etch, because you can ensure that you're above the sputter threshold of one material and perhaps below another material. I think I've sped up ever so slightly just as aware of the time. You can also process at different temperatures. Again, Christoph gave a very nice talk on that, so I'll be very brief here. So you can use very low temperatures, and this can be used to control undesired side reactions and chemical reactions, so it can help with achieving very vertical profiles. So for deep silicon etching, for cryo deep silicon etching, you get these very straight profiles. So in comparison to Bosch, where you get kind of scalloped profiles, with the cryo process, you get very smooth vertical sidewalls, the downside being the etch rate slightly slower, but if you're targeting very smooth films, it's ideal. And by going to cryo temperatures as well, you can also increase absorption of reactive species on surfaces. So there's a lot of interest at the moment of using kind of cryo HF processes for CMOS applications of etching silicon. So by doing it at very low temperature, you ensure that you have a lot of a lot of the chemistry available at your etch front, and you're not having to rely on it diffusing into these very high aspect ratio features to enable the etching. Conversely, though, there's also instances where we want to go to higher temperatures. So a good poster child for this is etching indium-based materials. So typically indium forms very involatile species, especially with indium chloride. So you can see in the bottom right here, etching indium phosphide at different temperatures. And we see that at low temperatures, we get very rough surfaces and a very sloped profile. As we go up to higher and higher temperatures, we see that we get much better profile and also much smoother surfaces, because it's much easier to volatilize the etch product. So this just nicely shows that there's different ways you can tune it using temperature. Thinking about what process challenges there are and what things you have to keep an eye out for. There's so many to go through that I can't really do justice to naming all of them, but I've named a few of them here, and you can see them schematically. So there's a very nice paper that came out 2 years ago now, which goes through a lot of the different challenges and opportunities there are for reactive ion etching. So I really recommend checking this paper out. It's basically a who's who of reactive ion etching, the authors on this paper. But you can see some of the issues that you have, so you can kind of get this variation in profile, deposition on your mask, undercutting, distortions, tilting. So it's an aspect ratio dependent etching, I mentioned earlier. And one of the interesting things people are looking into a lot now is whether we can use modeling and simulations to try and explore how we can optimize around some of these process issues that we're seeing. So using things like digital twins, like Monte Carlo simulations. So simulating your etch and then trying to kind of work out what will be the optimum conditions to use before you then go and try it experimentally. So we'll speed up a little bit the process development and process optimization. So we're wasting fewer wafers trying to get to the ideal process. Yeah. Similar to ion beam etching, I'll end with when to stop etching. So for reactive ion etching, people typically use in situ diagnostics. So they use laser interferometry. And here you're looking at reflections from different layers in your material. So this is very useful if you're working with transparent material. And so you'll see these kind of fringe structures. So for example, for lithium niobate, we know one of these fringes is about 143 nanometers of material. So we know if we etch one fringe, we've etched 143 nanometers. Downside is that you do need a spot in the middle of your wafer on which to kind of focus the laser onto. So the diameter of the laser is about 35 micrometers, I think. Typically, we suggest a kind of 100 nanometer wide, just to kind of make sure that you're able to easily find the spot. But it does mean that there's a small patch of your wafer where you're not going to be able to make devices out of to allow for the in situ measurement. And we can also do reflectometry. So this is very useful for non-transparent materials like titanium, like metals. And this is very good at telling you when to stop, because it will tell you when you've etched all the way through the layer, because there'll be a big change in reflectivity. And that's what we're seeing in this figure in the top right here. So we see as a function of time, reflectivity of the surface, and we see that as we etch through the metal layer, we see that the reflectivity drops off. So we can stop etching. And this can be automated to the tool. So the tool, you can set it running, and when it sees that drop, it will know to stop etching. Similar to iron beam etching, you can also use optical emission spectroscopy. So the same principles apply there. When you start to see no more species from the material you're etching, or you start to see species from the material underneath the material you're etching, you know that you need to stop the etching there. So yeah, you're either monitoring a decrease in your reaction products or an increase in the etching species you're seeing. What's nice about the OES as well is it can be very useful for monitoring your chamber health. So if you're doing chamber cleans, polymer, chamber walls, an oxygen plasma, you can track the carbon and you'll see that decrease and eventually saturate as a function of time. We do also sometimes see people using spectroscopic ellipsometry to track reactive ion etching. This is not too common, so it's more often used for atomic layer deposition systems, but it does allow kind of real-time monitoring of your film thickness. But it does require some quite specialized mounts. So the main processes that we typically see people using to monitor their etch are the laser ellipsometry and the OES. So in summary, RIE is a very versatile process. So it's a workhorse for micro and nano fabrication. There's many different process knobs that you can tune to optimize your process, but you do need to be very wary that you're not actually causing damage to the film as well. Similar to iron beam etching, there's three main types. So there's the planar RIE, the ICP RIE, and deep silicon etch. And RIE is ideally suited when you're trying to etch a specific target material. So it's very good at tuning the selectivity targeting material in comparison to iron beam etching, which will quite happily etch through lots of different materials. And with that, I'll move to the atomic layer etching part of the talk, and hopefully I won't run out of time. So it's interesting to think about, and I think Lena talked about it a lot, of kind of what's happening at the etch front as we're doing, as we're impacting upon our surfaces with plasmas and ions. And we typically see that as we increase ion energy, we see this increasing kind of disorder and contamination occurring in our films. So I showed this earlier. So for example, with gallium nitride etching, we saw that roughness and damage inherent in the surface. But what ALE aims to do is try and decrease the ion energy that we're using and allow us to do much lower damage etching. So you can see here in comparison, the film etch with atomic layer etching, we maintain the crystalline structure of the gallium nitride, and we're also not degrading any of the crystalline structure of the algal as well. So this nicely demonstrates how ALE can be a versatile tool to really scrape away that kind of last layer of material that you need to remove. I think ALE at the moment is a much newer technique than some of the other ones I've talked about, so iron beam etching and reactive ion etching. But ALE will be extremely useful for any application that's hampered by rough surfaces and interfaces. So we see this across a variety of different application spaces, from lithography and patterning, where you want to reduce your line width roughness and line edge roughness. For optical and photonic applications, you want to make sure you have nice smooth sidewalls, as that's a big source of loss. For micro LEDs, they quite often see this interficial layer on the sidewall of the multi-quantum well after they do the etching. So ALE could be a very interesting way to kind of remove these kind of damaged layers. Similarly, for power semi and RF applications, they quite often get these defective. So I showed in the previous slide that GaN layer. You can quite often get defective layers in these 3-5 materials. For quantum devices, it's extremely important to make sure you reduce roughness because and reduce contamination, because any roughness and contamination will couple into your qubit and reduce your coherence time. And of course, also for logic and memory applications, it's really important there as well. And we're actually already starting to see some ALE processes being applied in high volume manufacturing. So it's nice to see it following a similar trajectory to ALD. The basics of an ALE process. So I thought people might be less familiar with this, so I thought I'd give a bit more of an explainer of how it actually works. So ALE is a process of sequential self-limiting half cycles. So in the first half cycle, you aim to modify the surface of the material and create a thin modified surface layer that you then remove in the second half cycle using your etching half cycle. And you target having very high selectivity between the modified material and the bulk, such that when you've etched through the modified material, you stop etching on the bulk material underneath. And so by switching backward and forward between these two chemistries, you're able to achieve a very high level of controlling etch. The way I sometimes think about it is if you took a reactive ion etch process and split it in half, that's essentially what an ALE process is. So it's splitting out your kind of chemical modification of the surface and your removal of material from the surface. But ALE enables some great process metrics. So it gives you kind of sub-nanometer thickness scale control, wafer scale uniformity. It minimizes aspect ratio dependent etching because of those self-limiting half cycles. And we typically see that it provides surface smoothing and removal of damage layers, as I showed in the previous slide. The key process metrics for ALE are typically looking at saturation. So this will be saturation of both of your half cycles, so making sure that as you do longer and longer exposures of your modification, you don't see an increase in your etch cycle. The synergy of your etch process, so how true of an ALE process it is. I'll go into a bit more detail about what I mean there in a later slide. And then also the ALE window, so making sure you're in a process space where you're getting a reliable etch per cycle, and you're not etching into the bulk material, and you're not leaving behind some of the modified layer as well. For an ALE process, one of the key metrics to look at is that saturation curve I mentioned. So you can see if you were to develop an ALE process, your saturation curves you achieve probably look something like this. So we see for the modification half cycle, if you don't dose enough material, you'll be in this under saturation regime. But if you have a long enough dose time, you'll reach saturation and get a nice reproducible etch rate. It's also important to look at your saturation curves for your purging steps, because if you don't remove the chemistry from the modification step before starting the etching step, you'll actually enter this parasitic etch regime. So you'll end up having a higher, non-repeatable, non-uniform etch going on. If you sufficiently purge away the material and start the etching, you'll be able to get a nice uniform film. And then similarly, the same applies to the etching steps. You want to be in the saturation regime for parasitic etching. The great thing about the cyclic process is that it does provide the process benefits that I've mentioned, but it does come at the cost of very low throughput, to the point that some processes etch at less than a nanometer a minute. So these ALE processes are typically reserved for applications with really smoother, low as possible. I should say some people are also trying to target these soft saturation ALE processes as a way to try and get the benefits of ALE and mitigate some of the throughput issues they're having. And this is typically called quasi-ALE. It does still provide a lot of processing benefits, and it's slightly faster, but yeah, you might not get quite as good a uniformity in your etching process. That's a little bit about saturation curves. People also, you also need to check the synergy of your ALE process, and this basically dictates how ideal of an ALE process you have. So in an ideal situation, if you just did your dosing modification step, you shouldn't get any etching because it should form this kind of modified surface and then stop. And similarly with the etching step, if you don't perform any chemical modification, you shouldn't get any etching of the bulk material. In practice, many processes don't have 100% synergy because they're not fully perfect. But typically we would say anything that has a synergy greater than 80% is considered ALE. And so the way you calculate synergy is you look at your full ALE etch per cycle. So if you do repeated AB half cycles, you then compare this to the etch rate if you just do, say, half cycle A repeatedly and just do half cycle B repeatedly. And you can see the equation. I'd highly recommend, if you are interested in reading the papers of Karen van Erck, because she very nicely explains a lot of the basic concepts of ALE as well as synergy. The last process parameter that I'm going to talk about is the ALE window. So this is the ion energy range where you have a constant etch per cycle, allowing you to get a very stable and etch process. So looking here in the top right, we're plotting etch per cycle as a function of the instant ion energy. And in an ideal case, you'll see this kind of nice flat profile. So we have, in terms of increasing ion energy, as we increase the ion energy, we'll hit a point where we start removing the modified material. But until we get to a certain energy, we're not actually fully removing this modified layer. So you might get some non-uniformity. Within the ALE window, we're fully removing the modified material, but we're at a low enough ion energy that we're not sputtering the bulk material underneath. And then as we increase the ion energy further, we see that we actually go into this bulk sputtering regime, and you actually start losing some of the benefits of the ALE process. So it's really important that we make sure our ALE process lands somewhere in the middle. One of the problems is though that our ALE, our ion energy distributions, in fact, are never perfectly monomodal. They're not a single ion energy. So the RF biasing that's typically used in ALE has a very broad ion energy distribution, and it gets worse as you go to higher energy. So we can see that in this figure in the bottom left here. As you increase the bias voltage, we get broader and broader ion energy distributions. So in practice, our ALE window doesn't quite look like a nice theoretical process. There's a little bit of a kind of bowing upwards to the process because you'll have your ion energy distribution span across this box. So those are the three main process steps that you have to characterize for atomic layer etching. I should also say that I think we should expand our ALE window to also look at the chemistry of your process. So there will be, by varying the chemistry, as we saw for reactive ion etching, you can change how your etch performs. And so you can actually find windows of ALE for the plasma chemistry that you're using. And you can also look at temperature as a way to tune to have an ALE processing window. So we see for things like silicon nitride, if you go to very low temperatures, you can get no etching, but if you go to slightly higher temperatures, you get etching. And similarly as well so if we look here as a function of temperature and etch per cycle, we see that we have an ALE window for the GaN, and below that ALE, below a temperature of about 150 degrees, the etching actually stops. So it's very similar to the ion energy window as well. So that was a kind of crash course in what ALE is. There's a few different process families as well when it comes to talking about ALE. So there's anisotropic ALE, and there's a few different flavors of that. So there's kind of generic conventional plasma ALE. There's also cryo ALE and bias pulsed ALE, and these are typically used for anisotropic etching. There is also isotropic ALE. I'm not going to talk too much about that because it's not really a production-ready process at the moment. It's still kind of in academia and R&D. But it is interesting to think about. So it gives us, you have kind of general isotropic plasma ALE. We also have gas vapor ALE with plasma. So that's looking at just using gas phase species rather than things like TMA, which we often use isotropic ALE. There's also thermal ALE, which doesn't use a plasma. So I'm not going to talk about it because plasma technology, we're all about plasma. As a quick overview of the ALE literature, so if you're not aware of it, there's a nice ALE database that's run by the Eindhoven University of Technology. This nicely collates all the different ALE processes that we can currently find in the literature. And as we look at a trend, we see that anisotropic ALE is vastly more popular than isotropic ALE. So there's a lot more publications for anisotropic ALE, and this is because it's already kind of an established technique, qualified process used in industry. And isotropic ALE is still kind of emerging and trying to find its exact use case. But there's sport there. And just to hammer the high volume manufacturing point home, so at the ALD ALE conference last year, Dr. Shannon Lee from Samsung nicely outlined the kind of 12 different cases that they're using ALE for in high volume manufacturing and the different kind of materials that they're interested in optimize these processes for. So this is just to say kind of ALE is a newer technique, but so it's not as established as reactive ion etching or ion beam etching, but it is starting to kind of find its feet. And the benefits of using ALE. So I'd mentioned the downside is that it's very slow. But there are some benefits to it. So you get very smooth surfaces when you perform the etching process. So here they're looking at indium tin oxide, and the regions where they etch the indium tin oxide, they get much lower surface roughness as opposed to the layers that were covered by the masks. So they have nanometer RMS, whereas in the etched region they have half nanometer RMS. Similarly for the isotropic process as well, they see a reduction in surface roughness as they do more and more ALE cycles. The thickness control, so getting that nanometer scale control, we talked about it a bit earlier as well, but being able to accurately tune the film thickness that you achieve, being able to do this both anisotropically and isotropically. And similarly, it's very good for contamination and damage removal. So I showed this sidewall of a GaN, in-GaN LED earlier, but by using an ALE process, they were able to remove that sidewall damage. Similarly, for isotropic ALE, you can remove some of this. So they were looking at aluminum nitride, and they saw that the oxygen content of the film was reduced post ALE. So it shows it can help remove oxides. But when we take a step back and think about the things we want to optimize for our reactor design, there's just so many things to think about. So there's how you deliver your chemistry into the system, so how you get the precursors in there, how you co-react delivery, the vacuum systems that you're using, so the pumps, how you handle all the chemistry as well. So there's a lot of different things to think about when it comes to designing reactors. One of the nice things is that for atomic layer etching, we didn't actually have to think too much about the hardware needed for it. So fortunately, ALE is very similar to RIE. So the anisotropic ALE processes that we have typically are performed on our ICP RIE systems with a few upgrades to them. The two main ones for that are the fast-acting valves that allows us to do very short doses of the chemistry, half cycle A, and the bias power attenuator. So that allows us to go to very low ion energies and make sure that we're not damaging the material as we're doing processing. So the reactive ion etch tool is great because it can go to very, very low temperatures, but it can also go to cryo temperatures as well. So I think it can go down to, I think, minus 150, but also up to about 250. So there's a very large parameter space you can look at. And as I mentioned, at the end of the RIE section, there's already lots of endpoint detection built in. So you can track your etching very, very easily. I think what's also nice as a bit of a side note is that because you're doing your ALE quite often in ICP RIE systems, you can think about combining the two processes to get a best of both worlds. So I mentioned at the beginning how we want to make sure we're utilizing our full toolbox. Well, this is a great way to do that because you can, in the same chamber, do your reactive ion etch process. So this is great because it has a high etch rate. So you can etch the bulk of your material. So whether you're looking at making like a waveguide or etching down to some interface, you can do the bulk of your etching with your reactive ion etch process. The benefit that it's got a very high etch rate. Downsides are that you don't have the depth control, the selectivity, and you're potentially damaging the material. But if you stop kind of say 10 to 20 nanometers above where you know you want to finish your etch and then finish the etch off with an ALE process, we can see that we can get that nanometer scale control, get the better selectivity, and get the surface smoothing. Yes, you have a much lower etch rate from the ALE process, but you're only etching a few nanometers. So it's unlikely to actually add that much time towards your process. And it's being done in the same tool. So you're not even having to kind of take it out in a different system. And we're already starting to see people do this. So this is work from Kaust I showed earlier. And as you can see, they nicely remove that interfacial layer. And it actually translates into a better performing device. So it's quite hard to see in the image at the bottom, but they get slightly brighter LEDs by removing the sidewall. And then they get much lower reverse leakage current and much tighter spread. So you can see for the RIE process, there's a lot of device variability, but for the ALE treated device, there's much less device variability, much lower leakage. So that was just a bit of a side note on one of the benefits of doing ALE in an RIE tool. And when it comes to the hardware needed for isotropic ALE, so this is something that people are thinking a lot about at the moment. So I mentioned isotropic ALE is a newer technique, and at the moment, there's kind of a lack of dedicated hardware. The process requirements diverge quite a lot from what we look at in reactive ion etching. So we can't do what we've done for anisotropic ALE and just use the same tool. And this is because for the isotropic ALE, we're quite often using liquid precursors, higher substrate temperatures, longer exposures, and that's not really viable for the in the hardware that's been designed for the RIE process. We see, for instance, at the University of Boulder in Colorado, the University of Colorado Boulder, they have this really elaborate home build system. They do some really great research on that. I highly recommend you check out Stephen George's group there. They're great at ALE. And then similarly in Eindhoven, we use a lot. Eindhoven uses a lot of home built systems as well to do their ALE. And the focus is really on the in situ diagnostics and these home built systems to try and understand it at the R&D stage before companies then look into kind of how we would make hardware for this. I'll talk a little bit about the necessity. So I mentioned the fast-acting valves and the attenuator, and I'll mention a little bit of the necessity of why we need this. So here we're looking at OES analysis of a CHF3 pulse. And so with ALE, we're typically using very short pulses. And if you use a conventional gas box, we actually see tracking by the OES, the plasma species. We see that we actually get quite a variable dose by using a conventional gas box, but we use very short 20 millisecond, 40 millisecond dose times sometimes. Whereas if we use the fast acting valves, we get a very nice, you can see the intensity is pretty much constant for every single pulse of the CHS3. So it provides us this very short burst of gas into the chamber, which helps with process uniformity, process repeatability, but also helps make sure we have very low residual gas levels in the chamber because we're not overdosing and not having to do longer pulse times to compensate for this variability. We can get away with very short. Similarly, we want to use the low power attenuator because we want to get very low ion energies typically for ALE. So as I mentioned, as you go to higher energies, you get this kind of spread. But at lower ion energies, you get more kind of nicely well-defined ion energy distributions. And so by going to these lower energies, we can accurately land our ion energy distribution within the ALE window. And therefore, we're not going into that continuous bulk sputtering etch regime. We're staying nicely within our ALE window and getting very reproducible etch rate. I will mention that people are very interested. I mentioned tailored waveform biasing for reactor line etching earlier, but people are very interested in it for ALE as well, because if you can get a very narrow distribution with your tailored waveform biasing setup, you can make sure that you're landing all your ions basically right at the threshold of your ALE window, and this will hopefully improve the throughput of your etching process because you'll have a higher sputter yield with the higher ion energies. Whereas if you're using RF biasing, you can have this broad distribution, you have slightly lower etch rates in that regard. Tailored waveform biasing will also help with achieving selectivity. So here we're plotting the ALE windows of a few different materials. And say you wanted to etch silicon selectively to gallium nitride, for example, you would have to make sure your ion energy distribution landed fully between 40 EV and 50 EV, because you need to be above 40 EV to etch the modified silicon, but below 50 EV to make sure that you're not etching the gallium nitride and getting nice. So your entire ion energy distribution needs to land in this 10 EV window, which with conventional RF biasing can. I mentioned earlier that the low bias powers can sometimes lead to this broad distribution in ion energies. Interestingly, I actually think this could potentially be a benefit of atomic layer etching. So this can allow you to smoothen sidewalls. So because you can kind of see schematically on the left here, when you have a very high bias power, you have a very directional ion energy, very directional ions from the plasma. But as you lower your bias power, you get a slightly broader trajectory. And what this means is that you can get ions incident on the sidewalls of features. And so people are now actually starting to demonstrate this. So this was work done by JPL. And what they were trying to do was smoothen and narrow down their silicon oxide hard mask before etching the tungsten silicide underneath. So what they did is they performed their ALE process, and there was a slight isotropic component to the etching. And what this did was it took their 250 nanometer wide pattern and narrowed this down to 100 nanometers. Narrowed it down to 100 nanometers with the benefit that it smoothened out some of the line edge and line width roughness, so that when they translated the etch into the tungsten silicide underneath, they had a more consistent profile of the structure they were after. So they were looking at, and you can schematically see that here. So looking at the width of the structures and the design width. So they see that using the RIE process, they basically just have a vertical etch. But with the ALE thinned process, they actually see that the width of the feature decreases. So 240 nanometer wide pattern, they actually ended up with only about an 80 nanometer wide pattern. And what this allowed them to do was, again, plotting the design width against the line edge roughness. So for the RIE case, they found that the line edge roughness always increased, whereas with the ALE thinned process, they found that it stayed basically exactly the same. So that allowed them to get very narrow, very smooth sidewalls. And you can see the comparison before and after etching as well. So this is the silicon oxide hard mask, and this is the tungsten silicide underneath, and they get a very, very smooth line edge and line width roughness. And that's great for their application, as it meant that the devices that they were looking at, so superconducting nanowire single photon detectors, they didn't latch and basically stay on once they detect the photon. this really helped them achieve what they were trying to do. So a conventional anisotropic ALE process looks something a little bit like this. So you'll, as I mentioned, have your two half cycles. So you'll have a kind of chlorine dose, which is your modification step. You'll then have a purge where you have no chemistry. And then you'll have your etch step, which is using the substrate bias. I mentioned at the beginning, it's very important to do your saturation curves. And you can see that this is real data. I've taken the axes off it, but you do see that the ALE process, so as a function of Cl2 dose time, we see that the etch rate saturates very nicely. So we can dose as much Cl2 as we want, but we don't see an increase in the etch rate. Similarly, with the argon plasma time, if you tune your process correctly, you'll see that you can increase the argon etch time, but you won't actually see an increase in the amount of etch per cycle you achieve. We see a nice linearity in the etch rate, so you get a very controlled etching. There's a slight delay, so for some time, for some materials, there can be a little bit of a delay or an onset in etching because you've got to punch through an oxide layer before etching metal underneath, for example. But you get a very nice linearity in etch rate. And similarly, we can nicely see the ALE window. As I mentioned, reality is sometimes not as nice as the theory. And so we do see that slight trend up in the ALE window before we actually cross the Speller threshold bulk material. But it does nicely show that, yeah, you can experimentally see the ALE. There's a few different dosing regimes. So as I mentioned, you can kind of vary what whether you turn the ICP plasma off during your purge steps, or whether you leave it on, or whether you only have the ICP power on during the etching step. So you can do a kind of gas phase modification. So you could just dose chlorine gas and then only have the plasma during the removal step, or you can use chlorine plasma as the modification, also plasma removal. People are also looking at the low frequency pulsing as well for ALE. So I mentioned for reactive ion etching, but there's a very nice paper from IMEC where they go into some of the detail of how this low frequency pulsing during your plasma can be a very powerful tool for controlling etch as well. We at Oxford Instruments quite often look at bias pulsed ALE. So looking at, so for this case, we were looking at silicon carbide and being able to etch this material very quickly. So the benefit of silicon carbide is it's got a very high sputter threshold. So if you're not applying the bias, the argon ions don't have enough energy to etch the modified layer. And what this means is you can basically cut out your purge and just control your ALE process by switching the bias in. The eagle-eyed amongst you may spot that I put quotes around ALE because it's not truly ALE to some extent. You do get very controlled etching and very repeatable etching. But you'll see that as a function of the argon etch time, if you increase it further, there's this kind of window where you saturate. But if you do leave the argon etch on for too long, you will start to see the etching. So there's kind of an optimized time that you have the substrate bias on, where you get that repeatable, controllable etch before you then end up actually etching. And this has been demonstrated for silicon carbide, diamond, and cerium oxide. And I should say there is a webinar on that as well if you're interested. I've already mentioned quite a lot that ALE is enabling further scaling. So we're seeing it popping up in high volume manufacturing just to minimize aspect ratio etching. So we can see for RIE versus ALE, it improves the selectivity. So you can, for self-aligned contacts, it's really great because you're not getting that corner rounding, which leads to shorts. You're getting a nice, basically straight sidewalls. And an interesting application as well is looking at sub 5 nanometer crystalline films. So this is a paper from a Korean group, and they show that you can get crystalline zirconium oxide by doing a thick deposition and using ALE to etch back to a thinner film. So just to kind of end with some examples from literature. So there's conventional ALE, which I've shown the algan, but it can also be used for metals like niobium and harder to etch materials like lithium niobate. There's the bias pulse process that I mentioned, and there's also cryo ALE. I haven't touched too much on that at the moment because it's still, again, kind of a newer technique, but it definitely will be a very interesting process not to play with, and looking at how optimizing temperature can allow you to really dial in your process to the specification. So that was for kind of anisotropic ALE. There's also isotropic plasma ALE. Again, it's a bit of a newer technique, so there aren't as many processes available, but you can look at things like modification ligand exchange. So the poster child of this is the SF6 plasma TMA chemistry. So you form a fluorinated surface and then etch the fluoride away selectively. There's also modification and substitution etching, where you again form a modified layer and then selectively etch that with kind of plasma process. So you selectively etch away, say, the oxide from a nitride. This is very nicely demonstrated by iodine nitride, where you get nice surface smoothing, whereas for the RIE process, there was actually surface roughening. And there's also etch inhibition and surface cleaning. This is a very interesting ALE chemistry. I won't go into too much detail, but essentially it's a continuous etch process that poisons itself. So you'll have some organic etchant that will come in, absorb a bit of absorb a small amount of the material, etch a small amount of material, and then absorb an etch stopping layer on the surface. So you can see that in this case, they used Chittock, and it forms this carbon etch stop layer. They then used ozone to remove that carbon species and were then able to continue the etching. And they were able to experimentally show that it was actually the cobalt ACAC that was coming off the surface. And people have shown that this very nicely works as an isotropic. So ending again with when to stop etching. The benefit of ALE is that it's on the RIE hardware, so all of the in situ diagnostics are already available. So you can use things like in situ reflectometry. So we've demonstrated that you can very accurately stop your etch with 5 nanometers of material left, plus 1 nanometer. And you can, depending on the thickness that you're targeting, you can target 15 nanometers, 10 nanometers, 5 nanometers, just by looking at the reflectance trace. And this is great because it's kind of independent of the starting thickness of the film. So say you had some non-uniformity in the thickness of the material that you received, you would still be able to accurately stop with 5 nanometers left over. In principle, I think it's interesting to point out that if you have an established ALE process, you can actually sometimes get away with just saying, okay, I have an etch rate of 1 nanometer per cycle, and I want to etch 15 nanometers. Okay, I just need to do 15 cycles of ALE. So in an ideal world with a very happy set of circumstances, you can get away without any in situ monitoring and just rely on that very repeatable, reliable etch per cycle and make sure you end up with desired thickness. So in summary, ALE is an emerging technique offering sub-nanometer thickness control in very low damage applications. There's 2 main types. So there's anisotropic, which is more established, and isotropic, which still is kind of under development. And I should say that ALE is currently only really viable if you're wanting to etch very small amounts of material, but it can be combined with other processes to kind of enable the best of both worlds. And it really gives you process capability that you can't really access with reactive ion etching. So we kind of showed, I think I showed this image previously, but the comparison between reactive ion etching and reactive ion etching plus ALE is night and day. So you see the defective layer from the ALE is much thinner, and this translates into improving device performance through that interface. So just the RIE process, you have very poor behavior, but with the ALE process, you get very high breakdown voltage. And so that brings me to the summary. So as an overview of the different etch techniques, we have ion beam etching, very useful for multi-material stacks. It's great in that it can do very vertical etching, but it can also do slanted etches. Can use either an inert chemistry or chemical chemistry. It can either be inert or use chemistry to enhance the etching. Typically, we'd be looking at thicknesses from about 100 nanometers to 10 micrometers as the typical range that you'd use for ion beam etching. It operates in a temperature range of about 2 degrees. Reactive ion etching, very versatile workhorse of nano and microfabrication, huge process library, high throughput, very good repeatability. Can operate thicknesses of kind of tens of nanometers up to hundreds of microns. So for the deep silicon etching, for Bosch processes, you can get very, very deep etch processes, and it has a very wide temperature window at which processing occurs. so 150 all the way up to 400 C. And lastly, I just went through ALE, which is that newer technique, but it offers great process capabilities and kind of low damage, high selectivity, nanometer or angstrom scale control. You would be insane if you were going to etch more than 200 millimeters with ALE, simply because the throughput is so low. But it's great if you are targeting those very small film thicknesses. And because it's running on the same hardware, it's the RIE, you have the same temperature range. And I'll lastly end by saying picking the right tool for the job is vital, and no one of these techniques is a fix-all. It's very dependent on what your application is and what your target spec is. And with that, I'll end with some acknowledgements. So thank you to the wonderful applications team that we have at Seven Beach at our home office in Plasma Technology. So you can see a nice picture of all the guys in the apps team. I've stolen a lot of the images from this presentation. And also thank you to the ANNF and Michael for setting up the webinar and inviting me to talk. There's 2 QR codes here if you want to check out some more detail from Plasma. So we have our magazine and our webinar library. And with that, thank you very much, and I'm open for questions. Apologies, I went a bit long.
No worries, Nick. Thank you very much.